Il faut vraiment que je ne touche à rien.
Good afternoon, everybody. My name is Patrick Bruno. I am a scientist at ESRF and one of the organizers of the ESRF Webinars. Welcome to today's webinar. Before presenting today's speaker, I am going to just give you a brief announcement of future events. So next week, there will be a webinar by Alexandra Pacureanu on nanotomography. Then on the 13th of November, there will be a webinar by Marius Retegan on computational spectroscopy. On the 27th November, there will be the ESRF ILL colloquium, and it will be dedicated to mathematical modeling of COVID-19 outbreak by Neil Ferguson from Imperial College London. And in December, 11th December, we shall have a presentation by Paul Taforo. Title will be announced later. Before starting, I would like to give a few technical information. The talk is broadcasted simultaneously via Zoom and on YouTube, and can be viewed as replay on YouTube after at the end of the presentation. You can ask your questions by using the question and answer box, which you may use at any time during the presentation. And you can also view the questions of other participants to upvote the questions you find most important and you would like to be answered in priority. So we encourage you to use that whenever you want. And with this, I just also want to point out that this event is supported by the Streamline project of the European Union. So let me announce now today's speaker, who is Vincent Favre Nicolin. Vincent studied at École Normale Supérieure in Paris, and then he received his PhD at Université Joseph Fourier in Grenoble in 1999. Following his PhD, he did a postdoc at Geneva, at the University of Geneva, followed by a second postdoc at ESRF from 2001 to 2002. And after that, he was hired as a maître de conférence at Université Grenoble-Alpes. At the time, it was Université Joseph Fourier. He was there until 2015, and in 2016, he joined the ESRF as a scientist. Vincent also has a number of responsibilities. He's a co-editor of the Journal of Synchrotron Radiation, and since 2014, the director of the Hercules School on Neutron and Synchrotron Radiation. Vincent has received a number of distinctions. In particular, in 2012, he was appointed as a junior member of the Institut Universitaire de France. And in this year, he received the prestigious André Guigné Award of the French Crystallographic Association. And the title of Vincent's talk today is High Resolution Imaging with Coherent X-rays. And Vincent, the floor is yours. Thank you.
Okay, thank you very much for the introduction, Patrick. So I will be talking today about high resolution imaging using coherent X-rays. So this is a technique which has been developed a lot for the extremely brilliant source upgrade. And first I will begin by giving a very quick introduction about what are coherent X-rays. So if you go back to the definition which was given by Malcolm Howells in a series of tutorials 12 years ago, I mean, the coherence, we're talking about optical coherence, is going to exist in a region if you have phase differences between pairs of points in that region that have definite values which are constant with time. So you're just looking at the X-rays as electromagnetic wave, and you look at the phase. So you have two types of coherence. The transverse coherence, so if the X-rays are propagating in this direction, you look laterally at two different points, and you look at the phase of these waves, and if they are always the same relation, then it means that you have a very good coherence between the two. And this is related to a high brilliance and to a small source size, which is exactly what we are achieving with the EBS upgrade. And the longitudinal coherence, you're considering 2 points along the propagation direction, and you look at the phase relationship between these 2 points. And if you keep a close relationship, a very well-defined relationship, then you have a good temporal coherence. And this is related to the monochromaticity, and it's also improved by the EBS upgrade because we have more flux, and so we can use higher order for monochromators. So now, this is where we are today. I mean, we've increased the brilliance, so we have a smaller source size, so we have more coherent photons, higher transverse coherence, and higher longitudinal coherence because we can use silicon 333 monochromators. So I am not going to say anymore in theory about coherence, but we can look at what kind of applications we have. Now, what is interesting with coherent X-rays is that if we have a sample, like this one here, so you have a number of particles in a plane and an incoming wave. If this wavefront is incoherent, you see that the different waves arriving in time are very different, then you are going to obtain on your detector a scattering signal, but you are going to obtain only a statistical information. You see here you're going to obtain a ring, and this ring is characteristic of the average interatomic distance between the particles. Whereas if you have a coherent wavefront, so here in this case it's planar wavefront, then you're going to obtain the same figure, but with lots of speckles, so lots of small dots, which correspond to the, which are produced by the exact relative positions of all the particles. And this you're going to achieve if you have a sample which is smaller than the coherence length, or if you collimate the beam to a smaller size than the coherence length. Now, what can we do with this? There are two types of applications. The first type of applications is the study of dynamics. So you're going to follow this pattern, this speckle pattern, so the move of the dots as a function of time. And this is going to give you some statistical information about the displacement of the particles and their interaction with each other. So I'm not going to talk about this today, but this is one of the big applications of coherent X-rays. The other application is high-resolution X-ray imaging. So the diffraction image that you're going to obtain on your detector from this is going to be correspond to the Fourier transform or several Fourier transform, if it's in the near field, of the illuminated object. So if you can obtain the phase and the amplitude of this propagated wavefront, you can reconstruct the object in 2 dimension or 3 dimension. And if you are working with a detector which is far away, the resolution is going to be inversely proportional to the angular extent of a scattering. And this can give you very high resolution. And this is what is really interesting. So if you look at an object here, so we are sending an X-ray beam through this sample, which is the ESRF logo, and we look at what is happening, the diffraction pattern, the scattering pattern as a function of the distance. And you can see here that at the beginning you have more or less the same thing, but you can see on the left that you have a very different pattern if you use a coherent illumination compared to an incoherent illumination. When you go far away, For an incoherent illumination, you obtain something which is very fuzzy, but you cannot do anything from this information. Whereas from a coherent illumination, when your detector is far away, so in this case it's 1 meter away with small pixels, then what you're obtaining is a Fourier transform of your object, so you can reconstruct the object. Now there are different regimes that you can use for coherent X-ray imaging. So you start from your object, and then you can have several propagation distances increasing here. So these are in the near field, so you can still directly recognize your object here. It's just somehow blurred. And if you go much farther away, you will be in the far field and you get the Fourier transform of your object. So there are different family of applications here. The first important application that you can use is take just one propagation distance in the near field regime. And from this, you can reconstruct the object. This technique is called phase contrast imaging. It's a standard technique for imaging of objects. Since you only need to measure one image, you can do a very fast acquisitions. And also, if you have a wide beam with a long beam line, you can have fields of view with more than 1 meter. Okay, so you will have a very nice example of this kind of application when Paul Talforo is going to give his webinar in a few weeks from now. So I will leave you discover these examples with him. The other type of application that you can have is to use the recorded image at several propagation distances, but still relatively close to the object and in the near field regime. So typically 4 to 5 propagation distances. So you're going to be able to obtain higher resolution for the object from 30 to 100 nanometer pixel size. And you can have a field of view which is from tens to hundreds of microns, even a millimeter, but not in the meter regime. Then you can also use a single propagation distance in the near field regime, but instead of illuminating the entire object, you can illuminate part of the object, then move this illumination and record another image, and another one, and another one. And if you have enough illuminations with an overlap between the different illuminations, the technique that you obtain is near-field tychography. So just one single propagation distance, but multiple of illuminations, and you're going to obtain a higher resolution and a slightly higher quality than compared to holotomography. And again, the field of view is similar from tens to hundreds of microns. Now, if you go in the far field regime, so your detector is far away, the pattern is the Fourier transform of the object density. And then the resolution is going to be proportional to the angular spread of the diffraction pattern. So this gives you the highest resolution. You can go lower than 10 nanometers. Now with the current beam, we could just go to a few nanometers. Of course, the field of view is going to be smaller, from 1 to a few tens of microns if you use also tychography techniques. So for example, if you illuminate your sample at different positions but with an overlapping scheme, then you can image extended object. So we're going to look at all these different techniques, but they all have one common problem, which is a phase problem, which is a classical problem that have in crystallography. We record all these wavefronts on the detector, but of course we only record the intensity. So we know the modulus of a propagated signal, but we do not know the phase of a complex wavefront. So we need to recover the phase before we can do this inverse transform. Well, of course, we need complex algorithm to reconstruct the object. And for this, we need iterative processes to yield the highest resolution, and that's very computing intensive. So I'm going to give you, during this talk, a few numbers about the kind of speed with which we can reconstruct all these images, because it's very important that we can do this in time online during the experiment. I'm not going to go into detail about the algorithms because it would take way too long, but at least you will know what kind of applications and how much you can do with these techniques. So this is a phase problem, just very broad introduction. So you have the amplitude, the modulus of your observed intensity, and you're going to start with random phases. Then you can do, if you're in the far field, an inverse Fourier transform. If you have the right phases from start, you're going to obtain the electronic density of your sample. Then you can apply some constraints, like if you know that your object has a finite extent, that's a finite support, or if you know that the electronic density is positive, and then you can correct this, and then you can do a Fourier transform and go back to the detector space, and you can have an updated version of the phase it, and then you start again. These are Fourier cycling algorithms, and that's the family that we're going to use. But again, I won't say much more about this. Now, if we look at the different techniques which I have just presented, you can see here the field of view, which can go from a meter to the micron range. And you can see the pixel size, which can go down to just above 1 nanometer to fractions of millimeters or millimeters. And all these different techniques have different ranges. You can see that phase contrast imaging is for large objects. Near field techniques are in an intermediate regime, and for far field techniques are going to be used for the highest resolution. So if we begin with phase contrast imaging and holotomography, so these have been used for a long time with synchrotron applications. They have a relatively wide community. The algorithms are well known for, I would say, more than 20 years. And today the challenge is the data throughput. So for this, the ESRF is developing now accelerated software. So NABU is the new software which is being developed for tomography. And the PyNX, which is the software which I've been working on during the past few years, is also being developed to all the other techniques, and soon it will also be usable for holotomography. So if you just want to have a very quick example about holotomography, that's an example of brain imaging of, in this case, it's a mouse brain. And you can see here the different phase maps which have been recorded by rotating the sample. So you can see the projection of the object. And when you combine all these phase maps at different distances, then you can do an holotomography reconstruction, and you obtain a map, a three-dimensional map of your object like this, with lots of details about all the structure in the brain. I'm not going to say any more about this, because next week you will have a presentation, a webinar by Alexandra Pacurianu, and this is what she has been developing during the past few years, and specifically about brain imaging, and you will know all the details. The important thing is that you see here the range of that you can image. Here you have a pixel size of about 40 nanometers, and a field of view which is a few hundreds of nanometers. Now, if we switch to the next techniques. So if you look at near field ptychography, but also far field techniques, there's a smaller community. And the challenges during the past 10 years, 15 years, has been to obtain faster algorithms, but also robust algorithms to enable online data analysis. And this also has to work for the Bragg geometry. So let's start with coherent diffraction imaging. So if you look at coherent diffraction imaging technique, CDI, so this is what is done on the ID10 beamline at ESRF, which is specialized for these techniques. So you have a coherent X-rays, which are arriving on a sample, which can rotate around the vertical axis. And you're looking at the diffraction image a few meters away. And you just have one beam stop here. So once you have recorded all these diffraction images, after the rotation, you obtain a three-dimensional data set. And from this three-dimensional data set, you're going to be able to reconstruct the object. So here's an example of what has been reconstructed in the past few years. So these are COCCOLITHOPHORES, and which are producing cocospheres. And these cocospheres are just a few microns inside. So these are calcium carbonate, calcium carbonate crystals, calcite crystals. And you see they are composed of different coccoliths, which are assembled into a sphere. Now, these particles are extremely important because these organisms, these algae, are one of the most important calcifying organisms on Earth. So they are essential in the fixation of carbon dioxide, and of course they have a big influence on the climate. Now if you use, and this is also what yields this beautiful white cliffs on the seas of Cornwall. Now, if you look at an example of a reconstruction, this is what you can obtain if you look at one of these cocospheres using a scanning electron microscope. And this is the kind of reconstruction we obtain with three-dimensional coherent diffraction imaging. And you can see that the images are very similar. The only difference is that, of course, with CDI, you are obtaining a three-dimensional object. So you can cut this object in different pieces to know what are these different components, how they are assembled, what is their density, and so on. So you get much more information than just with a scan. Moreover, you can collect this for different samples, so you can determine a lot of diversity on all of the different samples, and you can learn much more about all the process which has produced these calcites and nanostructures. So this technique works very well, and the good news also is that the data analysis for this kind of application has become easier. So before the EBS upgrade, so the typical three-dimensional data set was about a pixel size of 512, and a data acquisition which could run into a few hours. And if you do a reconstruction with one GPU, now it takes 32 seconds to reconstruct this kind of data. Now, if you want to be sure to have a full validated reconstruction, and validation is going to take from 15 to 30 minutes from one of these datasets. But this means that during your experiment, you can collect your data, reconstruct it, and then you know what you have, you know the quality, and then you can go on with a different sample. So of course, after the EBS upgrade, so the new experiments are going to come, I think, in the next few weeks, we're going to move to larger datasets with larger detectors, with 1,000 and 2,000 pixels, and of course there will be a faster data detection. So there's a challenge for this data analysis, but the thing is you can come without knowing too much about the experiments, and this would work for you. Now there's still issues, historical issues with CDI, which is that algorithms rely on finding the object support. So this means that if you have an array which describes your object, you needed to determine what was the pixels, the voxels in which the object were. And to find the correct parameters, it was a bit difficult historically. And there was a lack of unbiased indicators to validate the solution. So this has been developed in the last few years by using a log likelihood figure of merit. So if you compare your observed intensity and your calculated intensity, you can use Poisson log likelihood like this to compare to estimate the validity of this diffraction pattern. But the problem is that the object area, so the actual support, so the number of parameters which make this sample is unknown. So there is always an ambiguity in the solutions. So what we are doing now is that we are setting aside 5% of all these experimental data points, which are masked to the iterative algorithm. So the reconstruction of the object is done without knowing these values. And then at the end, we calculate this Poisson log likelihood just by using these masked pixels. So this gives us a free log likelihood, which is independent of the reconstruction. And this gives us a more objective reconstruction. So if you start from this pattern here, this is a Fourier transform of the ESRF logo. You can see here 4 different solutions. And you can see here that if you compare this free log likelihood, the values for these 2 results is much lower here and here than for the other ones. So this means that this free log likelihood indicator is a very good indicator for the correct solution. And what is extremely useful for the data analysis is that you don't need to look at the detail of the analysis. You can just use this number to sort out the solutions. So this means that you can now do unsupervised reconstructions for all the data sets that you collect. And this is an example of the size, the number of pixels in the reconstructed object compared to the Poisson likelihood. And you can see here that this free log likelihood has a clear minimum here for a well-defined number of pixels. So this means that this is a very good criterion to find the correct solution, which is this one. There was an example application using this criterion. So it was actually done at Nanomax during the EBS shutdown. So you can see here, there are silver nanoparticles with partially random orientation, and they were measured with a coherent nanobeam on the nanomax beamline at max 4. And there are lots of those particles. So you had lots of diffraction pattern recorded like this one. But of course, I mean, to interpret all this data, I mean, when you have hundreds of diffraction patterns, it can be very difficult. So if you want to automatize this, you need this free-lock likelihood criterion to automatically sort out the solutions. So you can see here are examples of particles which were recorded, and there are examples of reconstructions using this approach and using this automatic selection. So in this case, what they did is that they did 1,000 reconstruction for each two-dimensional powder pattern, and then you keep the 20 best, and then you analyze them to keep just the best solution. So it means that you can really do serial coherent diffraction imaging, and you can do this in an unsupervised manner. And this is another movie, and this presents the cocosphere, which I showed before, and you can see here in a cut the object which has been reconstructed. So this takes a total of about 30 minutes on a single GPU. Okay, now let's switch to a different techniques. So the other very successful techniques which have been developed during the past 10 years is ptychography in the far field. Ptychography consists in illuminating one object, so in this case it's a Siemens star, different positions, and you record the diffracted intensity. And you can use a variety of algorithms to reconstruct. Now, one of the things that users are worrying about this right now is how you can do data analysis in a remote way, because you cannot come to the ESRF. And this can be done today using this address here, the Jupyter Slurm, which gives you access to an ESRF compute cluster during experiments. And you can see here, this is an example of analysis. So here you just describe the name of the data file that you're going to analyze and just describe the parameter for your beam. And then you can start immediately the data analysis. So you're going to perform a few, you're going to use different algorithms, different maps, alternating projections, maximum likelihood. And this is going to be used to optimize the object, which is illuminated by the beam, the prop, but also the positions, because we are scanning the sample, but there are a few errors on the positions. And you can see here that in a few seconds, and this is for 1,000 frames, you already have a very good view of your sample. You see the modulus, the phase, and you see here that there's a small mistake in the center, and this is due to the fact that the piezoelectric motors have some errors in the positioning right in the center. And when after you've started optimizing this, you can see that this small blur which existed has disappeared. And you see here that very quickly, you obtain the solution. And at the end, you also obtain, so this is the end, maximum likelihood. This is what gives the highest accuracy for the optimization. And at the end, you are also going to get a map of the error in the positions for your sample here. You see the maximum displacement is 150 nanometers between what the motor has been reporting and the actual position. And if you zoom in, you can see that there's a very high resolution. You see details, you see some holes in the structure of the Siemens star, which correspond to the real structure. So you can do this kind of analysis, even if you're not at ESRF. This also works. We have tools for this. Just to give another example. So, of course, we don't do just two-dimensional ptychography analysis. You can also do three-dimensional ptychography. This is done mostly on the ID60A BEAMLINE so far. And here you have this kind of analysis. Here you have, so each data set, so each projection of the algorithm consists of images of 700 by 700 pixels with 142 positions of a beam on the sample. And you repeat this by rotating the sample for 360 different projections. So this was at the time acquired in 35 hours. And now you can do the reconstructions with one GPU with 53 seconds per projection. So it takes about 5 hours if you have a single GPU. If you have more, then it can go much faster. So of course, this kind of experiments can go much faster and also at higher resolution now that we have the upgrade here. And you see here the example of reconstruction. So this is an interface between the peak and a polymer interface with a platinum layer on the top. And you can see the details of the electronic density in 3 dimensions for this sample. Now, okay. Now, of course, as we are moving with a brighter beam, with faster data acquisitions, we also want to be able to look at larger samples. Now, you can also do large ptychography datasets analysis. And for this, we have now developed a distributed analysis. So there's an example of data. So this is a modulator, which was measured on ID1. So there are 6,000 scan positions, and each diffraction image is 400 pixels wide. And the final object is 3,000 pixels in size. So if you want to do the analysis, taking into account partial coherence in the mode, it's not enough to have a single GPU. So you can actually distribute this data set. So you take all the positions on the sample here, and you see the different colors. It corresponds to points which have been sent to a different computer for the data analysis. So you split this in 12, and you can do this analysis in a relatively short time. And after this, you just merge your data. So the important news here is that you can reconstruct large data sets without a problem, and this is handled by our new complete cluster. You see here a zoom on one part of a sample. You can see the object phase reconstructed, and you can see that there are different parts reconstructed by different compute units, and you cannot see the problems, any problem in the stitching of the different parts. And you can also see the position shifts of a scan, because this was acquired over a long time, so there was a significant drift. So again, about 150 nanometers shift between the different positions. But again, this is correctly handled by the algorithm. So you can measure larger algorithms. And you can go much larger if you want. So this is the type of speed that you can achieve using the developments that we have made. You see, if you go up to 250,000 frames, analyzed on 12 different GPUs, one cycle takes a few hundreds of milliseconds. And if you want to do a complete data analysis, usually you're going to need a few hundreds of these cycles. So you can really go big. Now, another technique which is important if you want to image with a high quality is near-field ptychography. So it's the same principle as far-field ptychography, but you just keep your detector a bit closer and with smaller pixels. So again, you're going to reconstruct at the same time the object that you are illuminating and the beam which is incoming on the object. The advantage of this technique compared to a far-field technique is that you can image a very wide field of sample, wider than with a far field. So it should allow faster data collection, and also it's nicer for the detector because the intensity is spread on a wider area, and this has a number of advantages. And of course, you can use different magnifications, so you can tune the pixel size that you want from 20 to 50 nanometers, typically. The only drawback is that you have a slow convergence of the algorithm. So this is an example of a reconstruction which can be done using near-field ptychography. So this is a solid oxide fuel cell. So this is a dataset which was collected by Maxime Hubert, Jérôme Laurencin from Leti. And you can see here the size of the object. So this is about 50 microns in size. So you collect all these near-field ptychography projections, so a total of 1,200 projections. And for each projection, you collect 17 frames. In this case, we have a pixel size of 25 nanometers, and this is the volume that we have reconstructed. So it takes 10 minutes per projection for the reconstruction on average. And if you have 30 GPUs in parallel, it takes about 7 hours for the reconstruction. So it's still a bit long, but if you have enough GPUs, you can do this kind of reconstruction. Now, this data collection took 18 hours before the EBS upgrade. after the EBS upgrade, we will have much more data. And so it will go also much faster. Okay, now I just want to talk relatively quickly about the Bragg geometry. So if you want to do strain imaging, so imaging a crystal where you have atoms here, but with a displacement. So normally, the scattering that you obtain is the Fourier transform of electronic density in your crystal. So this is true in the small angle regime. So here you have the shape of your crystal here, and you have a Fourier transform of this object. And you can see the oscillations which depend on the size of the object. But if you go to Bragg reflections, so not just the small angle regime, then you see that there are distortions, and these distortions are the signature past 10 years, mostly led by Virginie Chamard in Marseille. And this can be used to determine the strain in nanostructures. And it has been very well adapted to the study of epilayers, but also for mollusk shells and other examples. So I will just show you one example of an analysis of a germanium tin disk. So this is this disk. So these are used as optically pumped germanium tin lasers. So they can laser up to 230 Kelvin. And of course, what is very important for the physical properties are the strain information in this sample. So you see here that there are different layers. I mean, the goal being to obtain the highest possible quality in this upper layer here of germanium tin. So in order to study the strain in this sample, and you can see here that there's a curvature here. This curvature here is due to the fact that you have an epitaxial synthesis of two different compositions of germanium tin. Now, what you're doing is that you're looking at this shape here, which looks like a mushroom, and it's actually bent, and you send the X-rays at one position here. So you illuminate a different position on your samples and you record the diffraction. And you can see here that for the different positions here, the scattering is going to be very different. In this position, it is centered. In this position, it's completely offset, and in this position, it's also on the side. Now, what is interesting is that because the sample is bent as a sphere, there's only a very small part of a sample which is going to be in diffraction condition. This means that you can do a two-dimensional analysis. And if you do this two-dimensional data analysis in tychography, you obtain this amplitude and this phase. And you can see here that there's a phase which is varying from the center. If you unwrap this phase, you obtain this curve here. You have a nice parabolic curve for the phase. And this can be related to the curvature of the sample. It corresponds exactly to a radius of curvature for the sample of 100 microns, which you can measure very accurately. And you can also see when you go in this direction here, that there's a change in the strain when you go through the different layers. So you keep its 11% germanium tin layer, and you go to this 13% germanium tin layer, and you can see that there's a change in strain. And this is still being studied, but it gives us a lot of insight about the physical information inside the sample. Okay, so now I'm going to conclude. So the takeaway message is that data analysis for coherent imaging has vastly improved. So both considering the speed, but also the robustness. And now with the ESRF-EBS upgrade, you can do faster experiments and at a higher resolution. So you have these different techniques: phase contrast imaging, holotomography, near-field tachography, CDI, tachography, and also the same technique in the Bragg regime. You can do these experiments. So some of them are still a bit complicated. If you want to do coherent diffraction imaging in the Bragg regime, you can only tolerate a few defects right now, but we're working on making this easier. And the Bragg tachography is also improving, but it's still complicated to analyze. It depends on the level of distortion that you have in your sample. But the other techniques are ready to use for anyone who doesn't need to understand the details of the algorithms behind. You just come, put a proposal, talk with a BEAMLINE scientist, and just focus on your sample. And that's what you should really do. So there are also, of course, other developments. I mean, you need to be careful depending on your sample about radiation damage, and there are some detector limitations. And so far, we also are working on doing faster experiments with continuous scans so that we can actually exploit the full speed which is of a full photon flux. Okay, so I want to thank all the people who have contributed to these studies and to all the data sets to improve data analysis. So of course, firstly, the ESRF BEAMLINEs, ID1, ID10, ID13, ID16A and B for test data and discussions. Also people from the data analysis in the software group, because I mean, we are using lots of tools, notably the SILEX tool for this data analysis. Also collaborations from the Institut Fresnel, from the CEA, Oxford University, Technion, Max4, APS, and David Pegelin at the Monash University. And finally, I would like to thank you for your attention. And if you have any questions, you're welcome.
Thank you very much, Vincent, for this beautiful presentation. We can now move to the discussion. There are already a number of questions in the question and answer box. I invite every participant to send in their questions. So we start with a question from Eduardo Machado Chari about 3D ptychography. Sorry, the question has moved while I was reading it. Why rotation of 360 degrees and why is it not enough to do 180?
Oh, I think that in the example, maybe I said 360 degrees, but that's not necessary indeed. And so in this case, it was 360 projections, okay? But you don't need to do 360 degrees, of course. 180 is plainly enough.
Thank you. Then there is a question from Mikhail Platunov about the possibility of using this technique or one of these techniques in the study of magnetic materials, magnetic imaging.
Well, now that we have more photon flux, then indeed it is possible to study magnetic diffraction. We actually have an experiment in a few weeks.
Can you elaborate a little bit?
But what you need to do is combine different measurements with different polarization. So you could use circular polarization in one direction and the other direction, and then combine these data sets in order to determine the magnetic structure of your sample. So this is an ongoing project at ESRF. So there have been already studies which are, I think, well known at PSI. But yes, we are going to exploit this. I mean, there's a project between the ID10 beamline and the ID1 beamline to also do this at ESRF. Of course, the big question is how fast we are going to be able to do these measurements, because the magnetic part of a signal is, of course, weaker than the normal part of a scattering. But now we have the photons to do this kind of studies, yes.
Okay, thank you. Then we have a question from Olivier Thomas about the influence of mechanical stability versus acquisition time.
Yes, this is also something that we have begun to address. So you see in the example that I showed you in the notebook analysis of ptychography, you see that the actual positions of the motors are being optimized during the reconstruction. So you can correct for any error which is occurring during the acquisition. And there are also schemes to do this, which have been proposed also in the BRAGG regime, and we should be able to use the same kind of techniques. So that's one way to correct this. The other way is to introduce, of course, is to have no motor errors. And for this, you need interferometry, and this is also being implemented. But it depends on the techniques you are interested in.
Thank you. Now there is a question by Jan Robinson about large field of view ptychography. What is the optimum number of probe position in each sub-area? And the stitching of areas together will never be perfect. As a comment.
Well, okay, it's a tricky question. If you should have enough positions on each sub area so that you can do a reconstruction. My advice is that when you have a really large data set, usually it's a 3-dimensional data set, So you don't want to go as fast as possible for one projection, but you want to go as fast as possible for all the other projections. So you should put as many projections as you can on a single GPU, and usually you're going to end up with at least a few hundreds of positions. And then if you want to make sure that the positions are stitched correctly together, you need to have some overlap. So in this case, in the optimization which I showed, I think there are about 5% of the positions which are shared between the different optimizations, so different independent optimization. And then the stitching, you don't see any mistake because you have this overlap, and it doesn't add too much to the calculation time.
Thank you.
And one other thing which is very important is that you should try not to have a too small beam, but you have to make sure that the size of a probe inside your Fourier window fills about 40% or 50% of your Fourier window, and this allows you to have a relatively wide beam, so you don't need too many illuminations to cover a relatively large area. That also helps because it means that one illumination is going to see different parts of the object which are going to interfere, and it is these interferences which are going to help the algorithm to converge.
Thank you. Then a rather practical question from COHERENT. For the free log likelihood, could we also apply this algorithm using PyNX as command line scripts?
Yes. If you do an optimization today of CDI datasets using PyNX, typically what you're going to do is that you ask for, you give a dataset and you ask for 30 optimizations, and you tell the algorithm to only keep, for example, 5 or 10 of the best ones. And this is going to be done automatically based on free log likelihood. So it's completely streamlined from the command line of PyNX. Okay, then there is a related question by Michal Ronowski. Are the codes for your data analysis available for use by other researchers? Oh, absolutely. PyNX is open source. So if you go to this address here, and you can download the source code. There was just a new version actually today, which was released. Thank you. There are also a number of questions concerning radiation damage by Eduardo Machado Charri. And the question is whether the repeated exposition for ptychography is a concern, and also whether there is special concern for biological samples, which are rather fragile objects. Yes, unavoidably, we are going to have issues if you try to image with too high exposure radiation sensitive samples. So of course, biological samples, I mean, we had an experiment a few years ago on bone samples, and on successive scans, we could see small changes. So you have to do an experiment, repeat it, and see if there are changes, but it's really sample dependent. So there is always going to be a limit about the quality that you can get for a certain type of sample because you cannot expose it too much. Thank you. Then there is a comment and question by Miguel Aranda, and this is about near-field ptychography. And Miguel says sample thickness can be important for the reconstruction, not only the field of view. And can you comment on the maximum thickness that is expected to be reconstructed? Okay, so right now, what has been done, I mean, the size of the samples which have been studied on ID16, I think the largest samples are about 50, maybe 100 microns. I don't think it has gone much farther. So you can do more. I don't think we have tried this yet at ESRF. And if you want to do this, then you need to change the algorithm. So this is not something which is available yet, to take into account this depth of field, because the beam, right now when we do reconstruction, we assume that the beam is the same through the sample, so through the tens of microns of a sample, and that it is not modified. But if you have a relatively thicker sample, then of course you need to take into account the fact that the beam is going to be changed, so you need to do the multi-slice analysis. And this is something which has been proposed at PSI. I don't think we're doing this yet, but yet these are among the things that we will implement at some point in order to take into account figure sample. I'm not sure what will the limit be for this. It will be hundreds of microns. I don't know if you can go in the millimeter regime. That's probably tough.
Then there is a question from some, well, anonymous guest, but we asked, what is in your view the best phase retrieval algorithm?
Oh, but that's a very broad question. It really depends on the technique. If you look at ptychography, typically you're going to do some combination of different maps, and then you're going to do a conjugate gradient maximum likelihood minimization. And that's what more or less everybody uses, I think, in production. And you can also debate about whether you want to use Gaussian noise models or a Poisson noise model, but that's the extent of minimization. When it comes to CDI, what we use normally in production is either HIO, so hybrid input-output followed by error reduction, and or air followed by error reduction. But you can also use different types of algorithms. I mean, when you converge, it functions nicely. I mean, you can use charge flipping, even the GPS algorithm is available. So I mean, there's not just one answer. It's very straightforward for ptychography because ptychography has the advantage of being a redundant technique, and the convergence is usually extremely robust. In the case of CDI, it can be a little more tricky because, for example, hybrid input-output, in my experience, I think is shaking more the dataset and can help convergence going from far away. But it's a little more unstable than, for example, AAR. So this is why, for example, in the ID10 dataset, which has a beam stop in the center, so we need to search in a relatively wide way, we use HIO, then error reduction by default. Whereas for BRAGG CDI, where we don't have a beam stop in the center, by default, it starts with AAR and then error reduction. So these are recipes, but you can play with them very easily through the command line. Just have to look at the documentation in PyNX, and then you can choose your own. It's very easy. You don't need to understand the programming. You can just try this from the command line.
We have a question from Mikhail Platunov about the issue of heat load on the X-ray optics at beamlines ID10, ID16, ID01, and how it would influence the experiment.
Okay, this is maybe not a question for me because I'm not, but I don't think that the heat load is much a problem.
Contact the scientists of these beamlines.
Yes, yes, I have not heard a huge problem about this recently since the upgrade. I mean, we have had cooling schemes for a long time, and what we have more today is not just much more photons, it's really much more coherent photons, and that's the big difference. So I don't think it's a particular, it's an exceptionally increased issue.
Photons, you need more photons altogether.
Not necessarily.
Question from Nili. How do you select the two solutions for the strain accuracy calculation? Is it randomly or differently?
Okay, so Nili knows a bit about PyNX. So in this case, so we actually use two independently measured datasets, and then we do the classical optimization with a number of solutions. Then we extract the main mode of the solutions for the two different datasets, and then we do the comparison. Actually, we're also combining different datasets, independent datasets on both sides before doing the comparison.
Thank you. A question from Laura Simonelli about the beam stability necessary to achieve the resolution that you have.
So of course, you need a relatively good beam stability, but if you think, for example, but this is also defined by the different slits that you have on your sample, and this is also optimized for all the different beamlines which are doing nano focusing and coherent imaging. So this is very well optimized. Now, if it happens that you have a beam which is slightly unstable, some algorithms, especially for ptychography, can handle this, because you are not reconstructing just the object in ptychography, you're also reconstructing the incoming wavefront, and you're just not just reconstructing a single wavefront, you are reconstructing different modes of a wavefront which are incoherent between each other. And so if you have variation, you can describe this being by these different modes. And this is something which was developed by Pierre Thibault and Andreas Menzel a few years ago in this multi-mode ptychography. And it works very well, even if you have some defects in your beam. But usually, when you do this kind of analysis today, I mean, you can easily have a first mode which represents 90% of the photons easily, which means that you don't have too many problems in practice.
Thank you. We have a question from Tunhe about whether holotomography or ptychotomography is easier to use.
It's okay. I think I'm not sure what to answer there. I think they're very similar. I mean, holotomography has been here longer. I mean, it's been developed since the end of the 1990s by Peter Klotens, notably. And it's been here a long time, so it's a very stable experiment. Near-field ptychography is more recent. It was, I think, the first experiments go back, I don't know, 4 years ago. I think they should be similar. My prediction, but I think Peter Klotens may not agree, is that I think near-field ptychography in the end should give slightly better results than holotomography and should probably supersede holotomography. But right now, if you want to do an holotomography measurement, you just need to measure for each projection 4 different images, 4 or 5 different images at 4 or 5 different distances, where for near-field ptychography, typically you're going to measure more than 10 images. So this means that near-field ptychography right now is still a bit slower because it requires more images. But when it comes to the reconstruction, I think near-field ptychography is still a bit slower in the reconstruction than holotomography, but it's a close call. And this is going to evolve as near-field ptychography is becoming a more mainstream experiment. So as far as you are concerned, as a user, I wouldn't worry too much. I mean, just talk to a beamline scientist, tell him what kind of sample you want to study and what kind of resolution you want and what kind of field of view, and then he will tell you what is the best technique. But they're very close to each other, and they're competing.
Thank you. Obviously, we could continue to bombard you with questions for another hour, but maybe at some time we need to stop. So let me just ask one final question, which is, you've discussed various techniques. Do they all have reached their limits, or is there a significant room for improvement of some of them? Where do you see the perspective for further improvements?
Okay, so this is the kind of thing that we are studying right now, because so far, I mean, coherent, for example, coherent imaging techniques in the far field, the limit has been the resolution around, let's say, 10 nanometers. Sometimes for 2-dimensional imaging, you can go to about 5 nanometers. And we want to go lower, probably around, the limit is going to be around, I think, something like 2 nanometers, but for relatively hard materials, radiation hard materials. And so we would definitely want to go over in terms of resolution. The other frontier is the time resolution, because we can collect data much faster now. And the question is, for example, if we can do 3-dimensional coherent imaging data analysis going down to a second resolution. And this is something which should be doable, but we have to see we have not tested this yet. I mean, we need to implement really fast data acquisitions, and we are still testing this. But I'm pretty sure that 3-dimensional coherent diffraction imaging resolution in the second regime is going to be possible. Right now, we have lots of photons. We are more limited by the motor displacement speeds than anything else. So, but well, we'll see. I think the coming year is going to be extremely interesting in this regard.
Thank you. I think it's time to close the discussion. So I'd like to thank again Vincent for this very, very interesting presentation. I'd like to thank all the participants in particular for their active and very interesting contribution to the discussion. I invite everyone to join us again in a week for the talk by Alexandra Pacoureanu on hard X-ray nanotomography. And we wish you a nice weekend. See you soon. Goodbye.